It's ridiculous. No? Yeah, it's stupid. So nobody is supposed to do it.
Good. Is that me or like? Okay, we're not seeing it on this one. But you should be able to. Oh no, it just stays there. Can you possibly like drag it up or? Yeah, looks like you can. Okay. Yeah, make yourself nice and comfortable, and then just move the camera a bit for you.
Is it also online?
It is.
Are people online?
We have about 7 people online. Yeah.
We need to be people. So
yes, I think so as well.
I can do that. I'm pretty good at it.
Okay. I have sent some messages, so I think hopefully, but yeah.
I'm sure anybody else will come to this site.
Yeah, I think so. So I think it's good to start. And well, the advantage of having such a small group is that we can have a really nice discussion as well. So I'm really looking forward to your presentation. If you can introduce yourself to the group, and we're very happy to have you here today. Thanks.
Thank you so much. Well, all of you know me. I am Alireza. I've been here for like 4 years now. Before coming to SRUC, I was working with Gregor's group, Highlander Lab, working on a project about simulation of dairy cattle breeding system. And now I'm working on a project called EnviroCow. It is funded by Bill and Melinda Gates, looking for solutions for reducing methane emission in smallholder dairy cattle in Africa, mainly in 2 countries, Ethiopia and Tanzania. And in this presentation, my results are mainly on Ethiopian data, not Tanzanian data, because the Tanzanian data was not available. They are coming soon. Good, and methane is a hot topic these days. And dairy cattle is one of the most important species that produce a lot of methane, and it's harms atmosphere, and there is a lot of research and money goes to see if the breeding of better cows for producing less methane is working or not. There is some successful stories, but here we are looking for if we can do this in a kind of very heterogeneous population in African countries. When I say heterogeneous, I will go into it through the presentation, and you'll see how the heterogeneous is. Okay, many different technologies has been introduced to measure methane emission. The first thing to reduce the methane emission in dairy cattle in terms of breeding is to measure it, and the measurement is the most expensive part of the game. And different technologies has been introduced to measure methane, from very expensive one, which is respiration chambers in the left downside, to the upside gold standard fart chambers, they call it. And then SF6 techniques, and the most popular one, which are using these days, which is green feed system in the middle, and our handy device, which is called laser methane detector. It is a handheld device that can be used everywhere, and it's easy to use. And we are using this device to measure our data in the population. There is a review paper by Sorg in 2022. All these different technologies has been compared. They have been compared in terms of purchase cost, running cost, labor, demand, repeatability, behavior alteration, and data throughput. Any of them has some advantage and disadvantage. The one that we are using here has low cost, low running cost, high labor demand, repeatability is low, behavior alteration is low to medium, and data throughput is medium. So this is the device. Different version of this device has been introduced. This is one, which I got the picture from internet, and it has a laser light to the nose of the cow and a guiding light, which you may see. This is the guiding light. It's not a laser, just to locate the nose of the cow to measure the breeze correctly. The data that we have gathered coming from Ethiopia is like 8,000 records. When I say 8,000 records for methane, it's really huge, and you cannot see that many records for methane emission in cows. These 8,000 records coming from like 700 animals. Many of researchers and publication are just based on a few number of animals or few hundred, but 700 animals with 8,000 records is really a good data set. They are coming from 25 different farms. Farm size are different from like 2 to 100. Data was gathered through 1 year, July 23 to July 24. And animals are really heterogeneous. They are heterogeneous in terms of age. We have heifers, milking cows, dry cows, old cows, young cows. They are in different stages of their parity, different parities, and they are especially different in terms of their breed. Or many other data that has been published already, they are usually from 1 or 2 breed. But this data that we have is from very local breed, pure local breeds from Ethiopia, to a very exogenous breeds like Holstein, and the management in different farms is very different. Some of them are very commercial, some of them is just a villager who keeps 1 or 2 cows. And alongside the methane data, we have mid-infra-red data because methane measurements are very expensive. People are looking for some proxy trace to, instead of measuring methane directly, using much cheaper measurement like mid-infra-red data, which is available in the milk. We have the mid-infra-red data, and the prediction that I show you in this presentation is based on the prediction based on mid-infra-red data of methane. The mid-infra-red data, there is like 1,000, usually 1,000 wavelengths. We take just 291 out of the 931 wavelengths. Why Ethiopia? Ethiopia is one of the countries that produce a big amount of methane in the world. Number 7 in terms of entry methane, which is coming from livestock. Ethiopia is located in the east of Africa, called Horn of Africa, if you have heard about this. And this country produces like number 7 in the world and number 1 in Africa in terms of entering methane emission. And another country which we would have data on is Tanzania, which is, I think, second or third country in Africa to produce entry methane. The measurements that we have from LMD, laser methane detector device, is based on part per million per meter. So ppm is not the methane production; it is the concentration of methane in a air or breeze of a cow. We need to transfer this ppm to like gram per day of methane. This is a formula by Lanzoni et al. 2022. They have to transfer this ppm to ppm concentration to gram per day. They have used CH4 peaks times some other peaks number, which is T dot volume, number of breaths per minute, the transformation value, which is milliliter to gram, and some other criteria that are mostly fixed. Just the T dot volume is somehow different in different cow. T dot volume is the amount of breaths that a cow can in one breath can have, and based on the cow weight, larger or smaller, they might have different, but usually the number is between 3,000 to 3,500, which we use 3,500 for our data. But this is using CH4 peaks. We just changed the CH4 peaks times the number of breaths to integral, because we have per minute, we have like 120 measurements of this methane. So every half a second, we have one measurement based on this device. And if you sum over all these point measurements, we have actual production of breeze, and then times T dot volume, transformation factor from milliliter to gram, and then another. So, and then this is per minute, and then multiplied by 1440, which is gram per day. The distribution of data in the population, gram per day, methane is like this. You see there is two bimodal distribution. This part is mostly represents the rotation of a cow, and this part represents the just normal respiration. And we have separate these two using bimodal normal distribution, which is this one. We call them respiration and rotation. We actually did analysis based on all three, but I don't know why. We feel like if we are one of the prediction of one of these, because of more homogeneous data might be better than global average, but the global average worked better, which still is a question for us too. So all the prediction is based on the global average of methane production, not the separation of respiration and rotation. And then we have mid-infra-red data. The 1,000 wavelengths are from around 400 nanometer to 4,000 nanometer. Every 4 nanometers, they take one point measurement of infrared data. It is around like 931, as I showed you before. But we don't use all of this. We only use 291 of them.
Yeah, so I think Pao says to use the mouse on your computer to point to things so that people online can see us.
Yeah, okay.
Thanks.
Yeah.
Perfect.
Oh, yeah. So we use these three parts of the wavelengths because based on literature, there is more information in these parts for predicting methane emission. So 291 of them out of 900 are used. And then when we take out this, like 1/3 of data, then we need to do some filtration of mere data to reduce fluctuations and smoothing the lines. Each of these lines is a record of one animal. And then we use the Savitsky-Golay filtration. This filtration is when we take out the first the 1/3 of data. Let's go here to that people online can see it. This is the raw data of 291 wavelengths. We haven't done anything on it, no filtration. And then we do the minimal filtration. I just call it minimal filtration. The standard filtration in the package, which is a package in R that does this filtration. Data would be look like this, and then some other high filtration still is there. You can play with the parameters and have another kind of filtration and compare the results, which one works better in terms of prediction. And then another one is just a scaled one in here. For us, the minimal filtration works the best for predicting methane emission. So I use the minimal filtration, and many other people are just using this standard minimal filtration using that package. Yes, we used the PLSR package, PLS package, and we used just formula CH4 mid-infra-red at the beginning. We did 5-fold cross-validation, 100 replicates, and the correlation between actual measurements and the predicted one was a range of 0.16 to 0.41. On average, it was a correlation of 0.29. And even so, 0.29 might be a bit low, but for a trait like with heritability of 0.2, if we standardize it, it's not that bad. And this is the distribution of the predictions in 100 replicates. Then we were thinking of adding more information to the model to see if the prediction improves, as there is a lot of publication that, for instance, milk yield has effect on methane production, or the age of cow may have some effect on the prediction, or body weight might have some influence on methane production. So we first decided to use the data coming from the milk-infra-red. Fat, protein, lactose, along with the wavelengths, are predicted from the milk-infra-red data. So we included these three to the model. And then there was some more data on feed components. Nitrogen, crude protein, NDF, ADF, ADL, and metabolite energy. You see the correlation between CH4, the first column, CH4, and these components are relatively positive or close to zero or relatively positive. So we included this to the model, fat, lactose, protein, and played with all different combination of them, body weight, milk yield. But unfortunately, there was no improvement in the prediction, which at the first instance might be because of the heterogeneous structure of data, that we don't have such a nice commercial settings that we can predict. But still there is room to dig into these components and see if we can improve prediction. And then that prediction was based on random cross-validation, as I said earlier. There is some publication, including this one, that talking about criticizing random cross-validation, and they say it might be over-optimistic. And we try to see if herd-wise cross-validation is doing the same job as random cross-validation or not. And we did herd-wise cross-validation, again, 5-fold cross-validation, 20 hertz as training, 5 hertz as validation, and 100 replicates accuracy was 0.03. This is expected, let's say. We have publication on this. Even this publication talking about 0, we had a 0.03, a little bit bigger than 0. But in our data, it's not only herd-wise cross-validation, it's the heterogeneity of our herds. We have herds, which is a villager having a couple of cows for his livelihood. And we have some commercial herds that have like Holstein breeds, not a local breed or not a crossbred. And I was looking at the age parity, lactation stage, and I stress on breed and management. These two are spatial in our data set. The others maybe exist in any other population, but different breeds and different management is something that influence our data heterogeneity. You see farm size was from 2 to 99. And when I was looking at the average CH4, average methane production per herd, and looking at the size of the herd that producing such a amount of methane, you can see there is some trends in methane production in big herds. Here, the big herds, they mostly fall through 270 to 300 gram per day. And they are herds with like more than 50 animals in it. But the herds that have smaller than 50 animals in it, they fall between 200 to 270. So it seems the size of the herd have influence on methane. But why size of the herd? Because when a herd is bigger, that herd means they need to have a better management. They need to have a different feeding system. They need to bring some efficient cows like the Holstein breeds instead of using the local breeds. So all of these things in bigger herds have effect on the methane production. So this is one of the reasons that herd-wise cross-validation might not working in our case. And then I looked at the inside cow, repeated measurement in one cow, how the coefficient of variation is. Normally, coefficient of variation of less than 30 is acceptable in data that we use in our analysis and prediction. But more than 30 always have some kind of influence our prediction. And you see here, more than half of the data have a coefficient of variation of more than 30. So it means inside the measurements of one cow, we have a lot of heterogeneity. So one cow in different states have different measurements of methane. So then prediction accuracy reduces because you cannot predict this cow is producing the same amount next time when you record this. So this is also one of the sources of heterogeneity that can influence on herd-wise cross-validation. Key takeaways: reducing the heterogeneity of population is a key. And if you want a good prediction, then you need to have a population with low heterogeneity. And using LMD is working, maybe not as good as some fancy technologies, but as much as you pay, you can. We have a phrase that as much as you pay, you can eat. So as much as you spend on it, then you can have accuracy. And this is funded by Bill and Melinda Gates Foundation with collaboration of SRC and ILRI, Nairobi, Kenya, Tanzania, and Ethiopia. And my boss is here. Rafael is the manager of this project with some other and many other people that I don't have picture of them. They are in the farm and they are taking the records. Yeah, that's my presentation. Thank you.
Thank you so much. I know that we've had discussions over lunch before, and really interesting to hear more of the details about your work. So for any of the online people, if you have any questions, feel free to raise your hand or send a message in the chat. And for everyone in the room also, any questions for Ali?
Yeah.
It's really interesting and to see that it's complicated when you have very heterogeneous data in herd. So did you do any analysis within a herd, like for the big ones? So just taking this individual and the prediction, even with standard cross-validation within that herd, try to reduce the heterogeneity in a way.
Yeah, it's good, but we need to have enough data. At least at the beginning, we didn't have enough data in one herd but now I think there is a time to look at this. But as you saw in the last this one, even in one animal, not in one herd, in one animal you have a lot of heterogeneity. Yeah. So and in one herd you see this is one herd. There is a lot of heterogeneity. For instance, this one produce from about 10 to 100. So even inside herd there is a lot of heterogeneity, but it might be a good
and is this
strategy too.
So is this heterogeneity within one animal, within a herd, is it linked to the time of measurements of the, or?
A lot of things are influencing time of the measurements, time to feed, time to milk, not the time of the day. And as I said, breed is in my opinion, breed is the most important one because I have been there. There is cows very local and producing a couple of kilos of milk, and a cow is producing 20 kilo of milk. So they are definitely different in terms of producing meat. So, and there is a lot of crossbreds and management, feeding system. Some of them, they just use the leftover food for their cows or they farm. Some of them are using mixed ratio TMR for total mixed ratio feeding. So these differences, and we saw there is some correlation between feed components and the methane production. So when you have such a big heterogeneity, then you might expect such.
Yeah, I remember it's long ago, but when I studied cow in nutrition, I remember that it's counterintuitive, but when they were eating grass, they were producing more methane because
Exactly.
there's
There
no
is some
vacuum,
publication.
so it's really quite feed, and you cannot correct for the feed, and it's complicated to like this into the genetics and feed and everything.
Yes.
Yeah. Cool.
Yeah.
So you mentioned that there's a low repeatability for the method for collecting the methane emission information. Is there a method that you could see working in these types of farms that would be better, that would have better repeatability?
Well, if we separate big farms from the small farms, anything you want to do in small farms is difficult.
Sure.
It's not easy to do. And prediction of things in small farms depends on many, many things. So if we exclude small farms and just focus on farms with higher than like 50 animals, then I'm sure there will be some improvements. I don't know how much, but there would be improvement.
Okay. Okay.
I can do this just excluding smaller farms, as suggested by, I don't remember her name.
Sorry,
Your name?
Timos.
Timos. So, yeah, one strategy could be is to just focus on some of the herds, not all of them.
And then the idea with the mirror data is, was it to find maybe a better, more consistent, like easier way to collect methane?
Yes.
Yeah.
Yes, because measuring methane even with this device, especially with this device, it needs a lot of labor work.
Sure.
So it needs someone to stay there for 5 minutes, locating the device light on cow's nose, and then results are sometimes not accurate. Cows are moving, and all these things influence on the prediction. But if we
Okay, one more question. So the mirror data, how often do producers get mirror data for their animals in Ethiopia?
well, I think I showed this. We use mirror data that has been collected plus minus 3 days from the LM data, methane data. Yes, a mirror of plus minus 3 days from the. So it means when we have a methane measurement, then we have one mirror measurement which is collected between 3 days, plus minus 3 days of that methane measurement. Yeah.
Okay.
Some other studies are talking about like even 6 days, plus minus 6 days. But the prediction I saw almost the same, plus minus 3 to plus minus 6 is almost the same. No big difference.
Do you have any other questions?
Well, I had a comment that was similar to the one from months about the finding smaller things. So you have a very heterogeneous population, but you are also adding several layers of heterogeneity from having heifers and older cows, and as you say, different times. And so maybe given the US such a big data, you say that according to literature, I'm not familiar with the topic in terms of size, but you could split it in several ways, trying to reduce heterogeneity in what you can control in a way, or at least and see if you can identify something that has bigger influence than others, like get all the heifers in once, or get all animals that are the first lactation, I don't know.
I haven't done this systematically, but just occasionally I saw when we have smaller part of the data, the prediction is better. For instance, at the beginning, there was just some of the herds were recorded, the big herds. Then the small herds came into the game. At the beginning, we had a prediction of 0.4 to 0.45. But as data came into more and more data came. Instead of increasing the accuracy actually decreased. That was because instead of adding more information, we add more heterogeneity. Yes, it definitely works if we split the data into sub-population, then the prediction will be better.
I have again a question about the heterogeneity. So is it the same person who's measuring in one given farm, or because
Two, it is two.
Okay.
Yeah, I have been looking at if differences in. No, there was no difference between the person because it is it's not measuring by hand or something that a person can influence on it. Maybe body weight or milk yield, someone just don't measure it or just expect it or just write something. But this device is some good thing with this device is that you can't do anything with the data.
Okay.
It is just the device, and if device is sets up nicely, then the person cannot have big influence. The only thing that they can do instead of measuring it in a cow, just put it on the air. But that is quite obvious that I can see this data is not meeting.
I'm going to ask you a few questions.
Sure.
I think I was just thinking, okay, this issue of heterogeneity of variance of the data, I think your model is still very simplified. Basically, we're looking at methane and then you looking at raw information. Well, why can't we not correct for the age and parity as part of the model, even the lactation stage as well? So I think we could actually make the model more comprehensive by accounting for some of these factors. For the breed, of course, we genotyping this animal, so very soon we actually know the breed proportion of this animal, so you can actually feed that into the whole system. So, but I think your model is, to me, still look too simplified, and I think we can make it a bit more complicated by fitting a bit more comprehensive model to the data.
You are right, Rafael. But my experience with the data is that even those are not as accurate as we expect.
Yeah.
I tried this milk yield and body weight.
Yeah, but
and you saw that there was no improvement.
Yeah, but these are variable, but it's most likely, of course, you're taking more information from July 2023 to 2024. So the cows themselves will be at different stages of lactation, maybe in the same variety, but they're just something we can model. We could try that.
Yeah, sure.
Yeah, the other thing I was also thinking about is, you're talking about the mid-infra-red, using 291 out of quite a wider range. I know you would have picked that because of literature, but you're dealing with a different population. Have you tried a wider range? Do you play with a different range and see whether that will actually improve the?
Well, the reason that they have taken these parts are because there is lower fluctuation in the data. You see, this part and this part and this part, you see some kind of, you can see the pattern and they might have information, but here, maybe, and here, you see, there is a lot of fluctuation in it and might not help. That's my impression why other literature didn't use this part. It's just, when I look at this, it might be just because of a lot of fluctuation and not helping. But yeah, we can try a different part of the.
Maybe the last one is, given that we have a lot of, well, I say it's a low repeatability measurement. So I think the idea was, hopefully, by having repeated measurement, you cancel out some of the noise. So basically, can you analyze it as a repeated trait? So basically, it's not the repeated measurements are not different traits are not different measurement in the same, but as repeated measurement of one observation. So in a sense, that will cancel out some of the noise.
Not as a repeatability, as average of record of one animal, I did this, but no improvement.
Something might be helpful.
I did the average of one animal.
Anyway, thank you very much.
Yeah. Good.
Any question online? We didn't see anything. No, I didn't see anything.
Yeah, there is something in the chat. Mm,
Maybe just comments from
yeah,
before.
this is from. Yeah.
All right, perfect.
Good.
All right, last call for people in the room or people online. If you have any further questions or comments, speak now.
No, never.
All right, looks like we're good. Thank you so much. This was a really great discussion. Thank you both to the people in the room for being here and for Ali for presenting as well. It's really great to see what SRUC is up to.
Thank you for inviting me. And
So,
yeah.
thank you so much. All right.
Next step, you get data from another, like you said, that's that.
Yeah, we have.